So Professor Orrit obtained his PhD in physics in 1984 at the University of Bordeaux in France. And in 1990, he pioneered first single molecule detection using fluorescence. Since 2001, he is leading single molecule optics group at Leiden University. Professor Orrit was awarded many awards, the Edison Volta Prize in 2016, Pinoza Prize in 2017, and he was elected as the member in Royal Netherlands Academy of Science and Arts in 2018. Professor Orrit contributed enormously in the field of photothermal microscopy. In 2010, he reported for the first time room temperature detection of a single molecule absorptions using photothermal microscopy. So title of his today's talk is photothermal. Okay, so Michel changed his title. So optical microspectroscopy of single molecules and nanoparticles. So Michel's floor is for you.
Yeah, sorry, I forgot to unmute myself, so I have to share again. Okay. Yes, maximize. All right, thank you very much, Subhasis, for your kind words. And first of all, I'd like to also to thank you for having me here. It's very unusual because I'm officially one of the organizers, but I should stress that actually Subhasis took the initiative of organizing this series of webinars and invited me, and he did all the work. So it's actually, I feel more like an invited speaker than a real organizer. This is the current composition of the group, and many of us do other things, not photothermal, but of course I will mention some other results as well. So you have the PhD students in the first two lines, a few postdocs, and my colleague Gert Kanters, who is emeritus, is also participating in our work. Right, so this is the outline of what I would like to tell you in 35 minutes. So I would like with an introduction on, why photothermal and when should you do photothermal, when should you look at fluorescence, when should you do just scattering, bright field or dark field. So I'd like to discuss that a little bit, and that is the basis of discussion for the whole series of webinars, I believe. And then I will zoom in a little bit more closely on photothermal detection. So what are the advantages and disadvantages, and show some examples, some applications. And the most exciting one to us in our group at the moment is the one on chirality that I will spend some minutes at the end of this presentation to discuss. Okay, so we are looking at single small objects, single molecules, single golden particles, nanocrystals, etc. You name it. Small things that will be small enough in my presentation to be assimilated to dipoles. So we look at a single dipole that usually is excited by an optical laser wave, that the blue wavy line here. And this wave may be heavily distorted sometimes. If you are in scattering samples, for example, this will not be a plane wave or even a spherical wave, but a more complicated type of wave. This wave may include reflections, scattering from defects in the sample, etc. And our sample emits its own scattered field, which I represent simply by a spherical wave issued from this point dipole, which will add to the incident field. So actually what you measure in optics is always in intensity. So you have to take the sum of two fields, the background field plus the scattered field, add these fields, square the total, and look at what you get. Of course, in general, you have three terms. You have the background intensity, the scattered intensity, and an interference term that includes both the scattered field and the background field. Well, now you can have different cases. Of course, the first case, which you have very often in fluorescence, for example, is that there is no phase relation between the incident wave and the scattered wave that you observe. Well, I call it scattered. It would be fluorescent in this case, but generally, it's a linear signal that goes in intensity linearly with the incident wave. So because there is no phase relation, we can forget about this interference term, and we just add the intensities. And that's okay, as long as your scattering intensity is bright enough. That was first discovered by Zsigmondy more than a century ago, and that was enough to award him a Nobel Prize a few years later. That's the so-called dark field scattering or ultramicroscopy, which allows you, provided you put yourself in conditions where this blue light is not seen, to see with a bright contrast the red light. Of course, this works as long as the scattered intensity is large enough. And for smaller and smaller particles, it doesn't work anymore. And we'll come back to that in just one moment. On the other hand, if the phase relation between these two waves is conserved, is well defined, then you have to take this term into account. And often, these scattered intensities were particularizing to very small objects. This scattered intensity is usually negligible in most of the cases for very small objects. And therefore, we have mainly two terms, the background intensity and this interference term. And provided this interference term is not zero, provided the phase is not completely destructive, you will benefit by looking at this term, because this term scales linearly with the field instead of linearly with the square of the field. All right, so let's go on. Now, don't take this slide too seriously, but it is a more sort of schematic of what happens in many cases for small objects only. In the case of fluorescence, as I said, you get rid completely of the background intensity simply because you put a filter that will get rid of the excitation light with a very, very high rejection ratio. And therefore, you can look at a scattered intensity, which is weak. It's normally photons, I mean, some thousands to hundreds of thousands of photons per second for a single molecule. So this is usually large compared to the background, and therefore you have a very large signal to background and a very large signal to noise. So that's why fluorescence is actually the workhorse method for single molecule observations, for example, in cellular biology. You can also go to dark field scattering, but dark field scattering, as I mentioned also before, then the background intensity is never really small if you don't find a trick to get rid of the background, for example, wavelength, or you could think of time or polarization, but those are much less efficient than spectral rejection. So therefore, it's very hard to get completely rid of the background if you don't use fluorescence. And therefore, usually the scattered intensity of small objects will be negligible against background. So you are in conditions where the signal to background is very small and the signal to noise is very small. And usually you cannot use dark field scattering unless you use fluorescence as a special case. And so you move to bright field scattering or iSCAT, or other techniques that I will discuss in a few seconds, where you have these two terms, and don't forget the phase relation between the two. So if phi happens to be pi over 2, then unfortunately this term disappears. But if not, then this term is advantageous, because what you need, of course, the signal to background ratio is still very small. The object is scattering very weakly compared to the background, but you look at the difference between the scattered intensity with and without the scatterer. And therefore, the signal to noise is what matters, because you can get rid of the background and focus on the signal and compare it to the noise in the background. And you will find out that, surprisingly, the signal to noise ratio scales independently of the background field. So one of the terms scales linearly with the field, and the noise is square root of the background intensity. It's also linear in fields. So that means the background field falls off, and you get something which is only proportional to the scattered field. It does not depend on the background. And that's very useful, because you can, in this way, adapt the reference wave, this background wave that you can tune very often, for example, by the reflection coefficient in the case of an interface, or by an additional field that you can send to interfere with your scattered field. You can tune this and adapt your intensities to your detectors, lasers, etc. All right, so now we are talking particularly on photothermal. So photothermal is a technique in which you use the heating, the absorption of one beam, the heating beam, to cause a change of scattered intensity with on the probing beam. So actually, this technique was first proposed by Professor Kitamori and Sawada in Tokyo back in the 90s, and later on it was, and they applied it in many experiments with microfluidics in liquid solution, and it was applied later in microscopy as well, immobilized objects like particles. So what we do in this technique is that we use this information, the absorption of the object, to detect the change of scattering. So in fact, what we have is a Chi3 effect. We have a crosstalk between two optical signals. One of the signals is the heating beam, and this changes the propagation of the probing beam. And any Chi3, be it electronic in origin, or vibrational in origin, or thermal, or maybe mechanical, you can think of many processes by which a Chi3 nonlinear susceptibility may arise, will be able to give you this crosstalk between two colors that allows to filter out very efficiently the scattered field, the scattered intensity from the background by, for example, modulating the heating beam and detecting only the scattered beam. So you have different techniques using this concept. For example, pump probe spectroscopy using pulses. Use the electronic component and also the vibrational component, and you can do pump probe spectroscopy of single gold nanoparticles, for example, or single quantum dots nanocrystals. You can also use stimulated Raman scattering. That was illustrated very nicely by the group of Sanishi back in 2010. And again, you can here use these electronic and vibrational components to modify, let's say, the scattered, the Rayleigh scattered intensity by your particle, which would depend on the electronic state of the particle or the vibrational state of the particle of molecule. And the photothermal component, the Chi3, on which we focus in this webinar. So this Chi3 has a response time, which is, whereas the electrons respond typically in picoseconds and shorter, the vibrations are more in the ranges of picosecond to tens of picoseconds. And the thermal effects, of course, have a large range of response times, which are basically from, let's say, nanoseconds to microseconds and even longer. This depends, due to heat diffusion, this depends very much on the area on which you look at the change of temperature. If you look at the change of temperature of the object itself, it will be very short, typically nanoseconds or shorter. If you look at the diffraction limited volume around your focus in a microscope, it will rather be microseconds, corresponding to modulation frequency in the range of megahertz, or, hundreds of kilohertz to some tens of megahertz. If you look at larger areas, which is done normally in more microscopic experiments, it can be up to seconds, even longer. So, for example, the mirrors of the LIGO interferometer were tested with photothermal techniques, and of course, the heating was on a very long time scales. So in the end, that's in conclusion. So we are based with photothermal techniques on a nonlinear process, and we use this crosstalk, and we use the fact that the background, usually the glass on which, or the solvent in which our molecules or particles are dispersed, is not active from the Chi3 point of view. This Chi3 is very, very small because we have no resonance. So we use this specificity of the thermal Chi3 to isolate the signal of our absorbing objects. And of course, as I mentioned, we rely on the modulation to subtract very efficiently the background, and in this way reject the scattered intensity that we measure in the bright field. Of course, the price to pay is that we rely also on the change on the index of refraction of the environment of the particle with the heating, with temperature. And this is usually a weak effect on the order of 10 to the minus 4 per Kelvin of heating. And therefore, we lose something in that way. I will come back to that later on. Right, so, but before discussing the technique itself, let me just zoom in very quickly on what is this heating, and in the case of nanoparticles, for example, which is shown here. So how can we measure it? I mean, how big is it? Is it an important effect? And this we have seen immediately in the case of optical trapping. Those were experiments done more than 10 years ago by Paul Weyrauch in the time. So he was able to trap a single gold nanorod at the focus of a near-infrared beam. And if you look at the nanorod, you will find that the signal, the scattered signal in bright field of this nanorod is actually fluctuating for two reasons. First, the nanorod is jittering in the focus of the laser, because the trapping force is, of course, restoring force but there are thermal fluctuations. So this is the long component that you see here. There's the translational diffusion fluctuations of the nanorod. And you find also much faster fluctuations if you work in polarization, which is done with black curve here. This component is due to the rotational diffusion of the rod. So the rod tends to align with the polarization of the laser. And again, due to Brownian motion, this angle will vary with time. And if you do a correlation function of the scattered intensity, you will find this very short component, typically in a range of a few microseconds. So much faster than the translation, which is a bit less than 1 millisecond. Okay, so now we can, you know the properties of your traps. You can plot these times, the rotational and translational diffusion times, as a function of the trapping power. And from the equation of the trap, you expect these blue dashed curves. And indeed, what you find is that there are very considerable deviations from these ideal curves, which are due actually to heating. So what happens at high heat trapping power is that the temperature of the water around the particle and the temperature of the particle is rising. And two things happen. There is enhanced thermal motion, so higher temperature, and the viscosity also decreases. The viscosity of water is very sensitive to temperature. It decreases with temperature. And from the global fit of all these curves, you can evaluate the maximum temperature change at the focus of the trapping beam with a maximum power of 80 milliwatt in this case to 80 K. So you see that these heating effects are completely non-negligible, are very big, and are easy to measure. Another experiment is more recent. It was done by Achilles Caratino in our group. So Achilles defended his thesis a few years ago. He's now his own boss in a small company in the Netherlands. And what he did is he looked at the photoluminescence spectrum of a gold nanorod. So this green spectrum is the photoluminescence spectrum of a nanorod when excited at 532 in the green. So you have the green spectrum with a nice maximum of the photoluminescence because of the enhancement by the surface plasmon resonance of the rod, the longitudinal resonance of the rod. But when Achilles put his laser, a 633 laser, in the wing of this plasmon resonance, he had the expected Stokes shifted photoluminescence spectrum, the red spectrum here, which is shifted to lower energy than the laser. But it could also observe the blue shifted anti-Stokes photoluminescence. So what does it mean, anti-Stokes? It means that you come with a laser photon which has this energy at 633, and you come out with a scattered photon which has, or photoluminescence, sorry, a photoluminescence photon, which has a shorter wave, that's therefore more energy than the incident photon. So this photon has been taking energy from the particle, from the bath of vibrations or electrons in the particle. It turns out in this case, it's mostly the lattice vibrations. And of course, there is enhancement. You see that the anti-Stokes in this case is larger than the Stokes. And this is because of the plasmonic enhancement. The density of states here, the enhancement factor and density of states is larger when you go to more blue, shorter waves than the laser wavelengths, and therefore there is a favoring effect for the nanorod to enhance the output at shorter waves. So because this is temperature dependent, you can fit now the profile, the function of energy or frequency of the photon or wavelength, the profile as a function, the density as a function of wavelength, and you can fit this with a Boltzmann profile, and therefore you fit the temperature. And the temperature you find is completely in keeping with what you can measure with your thermometer. So at room temperature, it's about 300 K, and it increases linearly with the heating. So again, we find the heating of some tens of Kelvin with the powers that we're using in this case. All right, so that means that the heating is there. Heating is easy to measure. So can we now use it for microscopy? So this is what is done in photothermal microscopy, or imaging of absorption by photothermal contrast. Actually, this work from 2002 was done with my former group in France, by Brahim Lounis and Philippe Tamara, on a technique slightly different from the one of Kitamori and Sawada, but which later on was superseded by the PHI by Brahim Lounis, and which we used also in the rest of our experiments. So basically, I will not go into all the details of the signal to background ratio. It's interesting to note, by the way, that if you would like to measure directly the absorption of a single molecule or of a single gold nanoparticle, you have to deal with saturation often. And in the case of nanoparticles, it's very hard to saturate, but you have to deal with photo damage or melting of the particle or reshaping of the particle. Therefore, that means that the heating beam is limited in power. There is a saturation. Because you need this wavelength to hit your object. However, if you look at the probing beam, and if you choose it in a range of wavelengths which the object does not absorb, then you can increase very much the intensity of that beam. And that means, because you detect that beam in the end, that means you can reduce in a way the shot noise due to photon noise on this beam by using a high intensity. And that's one of the nice features of the photothermal technique that I will come back to at the end of the talk. You can play on the two beams independently to solve a given problem in spectroscopy or in microscopy that you could not, or only with big difficulty, solve with only one beam. So you can decompose your problem into two problems that you solve independently with the two colors. In this case, for example, saturation with the green, and high signal to noise ratio on the detection with the red. All right, so actually the results I'm going to show, the setup was started by Alexander Gajduk and Mustafa Yılmaz, who is in the audience. So hello, Mustafa. Back in 2010, during Mustafa's thesis. And I will briefly show the setup, just briefly to describe what we do. It's basically the same setup we use to this day. So we have a heating laser and a probing laser that we overlap with a dichroic mirror. We focus this on the sample with an high-NA microscope objective, and we collect in the reflected geometry with the same objective. That's very convenient because you have to use only one objective. If you would like to collect in transmission, of course, you have to add another objective, symmetric from this one in the interface. And at the same time, you can use also this dichroic mirror to collect and measure the fluorescence. And here you have the example of a very nice point spread function. I should just mention in passing that the resolution that you can read with photothermal is slightly better than the one you reach in diffraction limited conditions with one beam, because the photothermal signal is the product of the probe intensity times the pump intensity, and therefore the point spread function is the product of the 2 point spread functions, and you win a little bit in resolution. That's not really super resolution yet. All right, and Alexander and Mustafa succeeded in measuring this single molecules of this very stable, photostable black hole quencher, a molecule which is used in molecular beacons to absorb energy and which is very photostable. However, I should say that that's a little bit of a piece of luck, because many molecules cannot withstand the kind of intensity that would be needed to reach single molecule sensitivity. The sensitivity of photothermal technique is about 1,000 times less than the sensitivity of fluorescence, roughly. And that means that you have to excite with about 1,000 times higher intensity to measure typically a nanowatt of absorbed power. And that means that the bleaching time of the molecules will be 1,000 times shorter than it is in most conditions, than it is in fluorescence. So 1,000 times shorter means really less than a second in normal conditions. So this molecule, being very stable and being in an oxygen-free atmosphere, they were able to measure these signals for seconds on end or even minutes, and they were able to really make sure that those were single molecules. Can we improve on this very weak sensitivity of the photothermal technique? The answer is yes, and is well known in the photothermal community for many years. It's in the book of Bielkowski, which is a classical in photothermal spectroscopy. You can move to a place in the phase diagram of a surrounding liquid around your object to be detected, where you have a super or near critical point. If you are close to the critical point, those are isobars, so curve of density against temperature at different pressures. And if you're close to the critical point, you see that the derivative of density, that is index of refraction, with temperature becomes nearly vertical. It becomes exactly vertical at the critical point. And that means that the slope, d and dt, becomes very large. And in principle, it can go a factor 1,000 in slope. Of course, noise also increases because you have such a thing as critical opalescence. So scattering also increases. But the ratio of the two gives you easily a factor 100 of gain in the sensitivity of the photothermal technique. And this was used by Lei and Tina Ding to improve on photothermal sensitivity and detect single molecules of MEH PPV. These molecules, this conjugated polymer molecule is very light sensitive. Of course, it absorbs light very efficiently. And when you have several excitations, a lot of photochemistry can happen. So if we would use the normal intensity we use in photothermal to look at these molecules, we bleach them in less than a second. However, by using the trick of near-critical xenon, it was possible to measure them quite accurately, both in the photothermal on the left here and in fluorescence. And of course, having these two pieces of information, you can do the ratio and measure the quantum yield. So here you see the two signals plotted against each other. So by making a ratio, you find that you find the quantum yield. What you find here, the quantum yield is correlated with the size of the particles. We found that the small particles have a tendency to have larger quantum yield, and we assign this to trapping in the particle. So if the molecule, if the conjugated polymer molecule is very short, there will be a very small chance that it has a trap. If it has a trap, we'll not see anything, so we're not counting in our statistics. If it has no trap, it's very bright. And the larger the piece, the larger the chunk of polymer, the larger the chance that you have one or more traps, and therefore the less and less bright it is. So you see it gives you a good signal, but the brightness would be relatively less large, less good for large chunks of polymer than for the small chunks. Right, so what happens if you, going back to this diagram here, what happens if you go across the critical point and you have this, you're in vapor or in the liquid, actually you start from the liquid and you heat, well, you actually will cross this liquid vapor equilibrium curve and you will make a bubble. So we have looked into that with Lei Hao and later with Thomas Jolans. So they both presented a PhD here, Lei, I think 5 years ago, and Thomas in 2020, almost more than a year ago. And what they did is focus the laser, the heating laser, across on a gold nanoparticle in a liquid, or water or pentane. And what you expect to see when you heat is to cross this coexistence curve, provided the particle is not too small, otherwise you'll be supercritical. But this was not the case in those experiments. And when this happens, you see that there is a huge change of index of refraction. It's no longer that like the vertical slope we had close to the critical point. It's really a jump, a discontinuity. And therefore, this bubble is very easy to detect. It's very bright compared to the contrast of index with the surrounding liquid is very large. And therefore, it was not even necessary in this case to do modulation. It was possible to follow the scattered signal directly as a function of time without any modulation and demodulation. So I pass on the details. It's very interesting to discuss that, but this is an example of the trace as a function of time here, real time of the scattered intensity. I should stress that the heating beam is continuous here, but you see that the signal is very noisy. I mean, it's not noise, it's actually point events, explosions, which is exactly what you obtain when you put your tea on the stove for boiling. I mean, there will be bubbles periodically exploding at the bottom of the pan, and this is exactly what you see in this in these plots. We have nearly periodic explosions, and you may also notice that each explosion is followed by one, and sometimes, if you look on the right down here, sometimes even three echoes. Sorry, one or two echoes, so 3 peaks. And actually, you can make out the diagram here and find out that these echoes are just reflections of the acoustic wave released on the explosion on different interfaces in the vicinity of the particle. So in this case, we had glass and oil and the lens, and we have reflections on these different interfaces. So this nicely illustrates that you can use photothermal in conjunction with photoacoustic microscopy. So in photoacoustic, people use normally acoustic detectors, but those have limitations in response times. So if you could couple optical detection and optical production, so you can use the nanoparticle both as a source and as a detector for acoustic waves, as is done here. You could also do a photoacoustic microscopy in combination with photothermal down to very small, short scales. Okay, so let me briefly mention another application of photothermal to plasmonic sensing. This is a work done by Peter Zijlstra several years back, almost 10 years ago. And the theory was done by Pedro Paulo, now in Lisbon. Peter is now in Eindhoven University in the Netherlands. And the idea of the experiment is quite simple. We actually look at single nanorod, we look at the wing for any optical observable. When a single molecule will stick to the rod, and this is done with a convenient bioconjugation, the plasmon resonance will shift a little bit. If we measure on the wing, we'll see a change of the signal. And this is what you see here. This without molecules in the solution, a stable signal, photothermal signal. When we have a low concentration and we increase the concentration, more and more of these events happen. And this allows us to detect in real time single molecule binding on the surface. I should stress immediately that Peter has now developed scattering instead of photothermal, which has several advantages, brighter and faster. And so we also looked at this more recently with Dr. Martin Basque in the group and a new PhD student, Nazreen Asghari. And both of them have been working on that. So what we do here in this case, we look at the gold, single gold nanorod, and we look at the plasmon resonance. And we work on polarization to enhance the signal-to-noise ratio. And the traces you see here are due to single 5 nanometer gold nanoparticles, which are diffusing in the near field of the nanorod. So they're entering and leaving without sticking. And more recently, it has been even possible with for Martin and Nazreen to look at single hemoglobin molecules and to detect them on the fly. Still, there is some sticking, as you see here. This molecule clearly adheres, or not binds, but sticks to the nanorod during a few tenths of microseconds. But some events are extremely short. This one, for example, is really a few microseconds. So in this case, we really think that this is just a purely a diffusion that can really detect these molecules on the fly. All right, so as a last illustration, I'd like to briefly mention the detection of chirality with photothermal contrast. And again, I will make use of this concept I said before. So we play on two different properties of the two different colors to solve a problem. And a very nice illustration about which we'll hear soon is the technique of Jichin Chen to look at the chemical infrared absorption spectrum of a sample. And in this case, you use a heating beam, which is in the mid-infrared, which is very hard to focus, with which you would have no spatial resolution whatsoever. But then you recover your spatial resolution from the visible probing beam. So you decompose your problem of spectroscopy in the mid-infrared and high optical resolution in the visible. And here we have something very similar. So we wanted to look at the chirality at the circular dichroism of a small particle in the focus. And as you may know, it's very hard to control the polarization of light at a focus with a large NA. So basically, if you increase the NA, you are most of the time screwing up the polarization. So it's not very favorable. And vice versa, if you want to have a very well-controlled polarization, it's much easier to do with a beam, an open beam, with a low NA, and therefore the optical resolution suffers, the spatial resolution. But here again, you can solve this problem by decomposing and having the probing beam with high NA and the excitation beam, the heating beam, with a high purity of polarization. And this is what our chairman, Subhasis, and the PhD student Patrick Speth have been doing this last few years. And they've been working in gold nanoparticles, which have been imaged by Wiebke Albrecht in collaboration with Sarah Bals in Antwerp by electron microscopy and tomography. So basically, the idea is also quite simple. Actually, instead of doing photothermal, we modulate the heating intensity. We just modulate the polarization state of the light. So we go from circularly right to circularly left at a high rate. And we look at the little change of signal, which is caused by different absorption of these two polarization states by an object, which is chiral. So if an object is chiral, it does not respond in the same way to circularly right and left polarized, and therefore there will be a difference, and that's this difference we want to measure. And this illustrated here in these pictures. You see gold nanoparticles, 100 nanometer in diameter. You see the photothermal image, so it's quite bright, of course. If you look at circular dichroism, the signal is about 100 times less, so still sizable signal. And you see, for example, 3 of these particles are circularly. They have a right-handed chirality. The other one has a left-handed chirality. You have to be very careful in these measurements that you really eliminate carefully linear dichroism. So we measured this linear dichroism for these particles. So nominally, if these particles would be spheres, they would have neither linear dichroism nor circular dichroism, of course, but they are not perfect spheres. They do have defects, and that's why we need to have the tomography to understand better what kind of defects they have. So if you carefully measure this linear dichroism, you can eliminate it, and you see that linear dichroism is usually much larger than circular dichroism. So basically, factor 10 between the absorption and the linear dichroism, and another factor 10 from the linear dichroism to the circular dichroism. So nowadays, in the last few months, Patrick and Subadis have enormously enhanced the rejection of polarization mistakes, and now they can measure asymmetries in the range of 10 to minus 4, a few 10 to minus 4. And they use this to measure the magnetic circular dichroism of nanoparticles, magnetic nanoparticles. Those are the magnetite particles which are used in bioassays to collect biomolecules from a complex mixture. And what you see here is without magnetic field, we have a given CD signal. When you go to let's say the North Pole, we push a permanent magnet close to the particles. These particles become more red. When we approach the South Pole, they become more blue. And so it was been possible in this way to measure the magnetization curves of individual particles. All right, so I think I have to stop very soon here. I just want to briefly give an outlook of what I find the most exciting. So, of course, circular dichroism measurements are very interesting, and we hope in the future to do that not only on particles, but also on molecules, maybe not single molecules immediately, but on small clusters of molecules. Contrast enhancement works with critical fluids. Other colleagues have used liquid crystals, for example. I'm sure there are many tricks that could be used. Recently, 2 archive papers were proposed to use fluorescence as an enhancement of photothermal. So I think many exciting developments in this field. I'm also excited by the mechanical effects that nanobubble can have, nanobubbles, and the coupling with photoacoustic microscopy. And of course, chemical imaging is a very important and exciting development of photothermal spectroscopy that we will hear about in the rest of this webinar, which I'm looking forward to. And I thank you for your attention. I'm ready for discussions and questions.
Okay, thanks, Michel. It was in perfect time. So yeah, you can ask question directly if you have any questions. And I think I got a question from in the chat, Adrien Girard. Can you please ask by yourself? You can unmute and ask.
Hello, Michel. And,
hello.
Hello, everyone from Paris. So yeah, the question I had was more about the anti-Stokes luminescence thermometry. And I was wondering if it can be applied to other materials than gold, and if we can use a monochromatized supracontinuum light excitation for measuring this, which is more convenient for fine-tuning the excitation wavelength than a continuous wave. But then again, we are pulsed, so I imagine that the photothermal heating are different than continuous wave. So
yeah, so the question is about the anti-Stokes scattering. So is it limited to gold, or I would say to metals generally? I think not, but I cannot prove it. Of course, it is heavily dependent on the plasmonic enhancement. So if you don't have this enhancement to, first of all, the photoluminescence yield is very low, typically 10 to minus 6 in the case of gold nanoparticles, and it benefits from the plasmonic enhancement. So if you don't have plasmonic enhancement, it's rather 10 to minus 10, so which means a very, very weak signal. So without this plasmonic enhancement, it may be probably difficult to detect, but I don't know, honestly. And the second question is, can you do it with a supercontinuum? Of course, you need spectral resolution. So you saw typically the kind of spectrum that we had. So I don't know how broad your peak is, but in supercontinuum you can of course filter. So you filter, if you filter your pulse so that it fits inside the notch width, there is no obstacle obviously to doing spectroscopy with a supercontinuum instead of filtered supercontinuum. It shouldn't be too broad, of course, because you need to eliminate very efficiently the heating beam to look at the weak photoluminescence.
Okay, thanks a lot.
Okay, we got a second question from Mahar Damardeh, if I speak rightly. So can you please ask?
Thank you for the talk. I got a question about your background. So you're looking for very tiny signals on top of a fluctuation, like a background fluctuation. And I was wondering if, like, what would limit your measurement? Like, how do you isolate your setup from, let's say, room temperature variations and stuff like that? Or can you comment on the background you typically work with? Or what is the smallest increment that you can change and pick up with photothermal microscopy?
All right, so I take your question and as a very experimental one. So how to get rid of background problems? As I try to show in my introduction, we have background. I mean, all these techniques, photothermal and IceCat and pump probe, I mean, all these techniques work on a very high background. So we are dealing with the background from our experiment itself. Of course, we don't want other background sources from the room lights, but usually those are not really a big problem in this kind of experiments. They are a big problem in fluorescence, in photoluminescence, because in this case, you are detecting very weak signals. And of course, if your room lights are on and leak into your detectors, then the background will be a problem. If you work with this kind of bright field techniques, the background is usually not a big problem because you have a lot of light anyway, and you're looking at a weak variation, weak changes of a large signal. So whether the signal is contaminated with a little bit of stray light, you don't mind too much. Right, so the main problem is how to isolate the interesting part of the signal which contains information on the particle from the large background. And you have different techniques. So IceCat is one of them. In IceCat, basically you do it by looking at the time dependence of your signal. So you have background. When molecule comes, the background changes, and you look at this change. In photothermal, you cause this change yourself by modulating the heating. So you subtract the signal with heating or the signal without heating from the signal with heating, and you make this difference with a lock-in amplifier usually. And you have many other tricks of this kind to isolate your signal, so that the background, from other sources is usually not a big problem.
I understand that. Thank you. But so in principle, you could, like in theory, you should be able to go and image an infinitely small signal. But you can't. So what limits you at the end of the day?
Oh, okay. So yes. So that's your. Why does dark field microscopy not work? That's your question. And what is the background source? That's
basically.
Yeah. So I mean, it depends a little bit on. If you do fluorescence, it works very well, right? That's because you can reject any background sources very efficiently by the wavelength. Now, if you don't use spectra. So if you use spectra and your fluorescence passes the spectrum and the background source does not, your problem is solved. So then that's not a problem. If you cannot use or do not want to use spectra, what can you use? You can use polarization, but it's very hard. Then you need to have a very, very high quality of the sample. And for example, the NA of your objective would be a problem. So you have to really control very well where you are in the focus and the quality of the polarization of the focus. You can use time. Time depends. You can excite with a pulse and then detect delayed with respect to the pulse. And you probably can use other techniques I'm not thinking of. If you use nothing, yeah, if you just send your laser and look at the scatter intensity, well, one well-known way of solving a problem is to place yourself in vacuum. So you can see single atoms in a high vacuum, and you have absolutely zero background because vacuum is not scattering light. Yeah, so it means the whole excitation beam is going through. There will be no off-beam scattered photons unless there is an atom or molecule, a small object. So that's one way. If you're in condensed matter, and let's not even mention a biological cell, all the environment is always scattering. We will have Rayleigh scattering, we have impurities, which are also there in the case of fluorescence, which will scatter. You have bumps and protrusions on the interfaces between different, and all of this inhomogeneity in the glass, etc. So all these little imperfections of condensed matter will give rise to scattering, and this is very easily orders of magnitude larger than the scattering of a single molecule, for example, not of a single gold nanoparticle, a few tens of nanometer in size. So that's strong enough that it dominates the scatter intensity for a clean sample. But if you're talking about single molecules, then almost any little defect of a real solution, a real interface of glass, will scatter more than a single molecule. Is that the answer to your question?
Yeah, I guess it goes to a more lengthy discussion, but thank you. That was very helpful.
Okay, you're welcome.
Okay, so maybe there is one more question. You can directly unmute and ask a question. So, Hall, can you please ask questions?
Yes. Hey, Michel. That is
Hi,
fantastic. I have a curiosity, actually. You mentioned earlier in your introduction that it's a Chi3 process. And then in the end, you talked about detection chirality. So I was curious, have you thought about using other nonlinear spectroscopy techniques to look at chiral processes combining photothermal spectroscopy, for example, if one could combine other Chi2 processes to look at chirality?
Yeah, okay. Thank you very much for the suggestion. We didn't think of that indeed, actually. So indeed, it's probably possible to use the properties of Chi3 to indeed, extract. Yeah, that would be a very nice experiment to do.
Chi3 is a symmetry invariant. Chi2 would allow you to go into the bulk. That's what I'm thinking. Sorry.
Yeah. I'm sure there must be something to do here. And the right person to ask on this would be Josis, who worked a lot on this kind of, anisotropic properties of all kinds of molecules and particles. And he's still active. And I think that Sophie Brasselet in Marseille is very much doing similar things with small particles. So that's indeed a very good suggestion. But for us, photothermal is just our Chi3 is very simple. It's just the NDT basically. It's just a variation of the Chi1 with the intensity applied. But you can of course look at more subtle tensor matrix elements than just that one. Thanks for the suggestion.
Thank you very much.